Hi, my name is Dhruv, Monga, and I'm here with Suematsu. We're here from Physical Optics Corporation. We're going to be presenting our software that we've developed under a Phase 2 SIBR. It's called the Avionics Compositional System of Systems, Simulation and Modeling Toolchain, or for short assist. I'm going to go through a quick background on POC. We're a small business founded in 1985. We've been mostly SIBR-based, but recently we're beginning to transition to more production. And then one thing I want to highlight is we have a large array of different products and areas of focus, specifically in airborne systems. We have several products that are very mature and some are currently airborne as well. So while developing this project, we used models derived from these flight-ready products to inform the development and then also test it as well. Do you want to take over?
Hi, I'm Suematsu, also from Physical Optics Corporation. I'll walk you through the problem we sought out to solve and our solution approach and the current and planned features of our product line. Okay, so what is the problem? In the past, avionics have used single core processors, and it's been difficult to validate processing requirements. And now that we're considering multi-core processors in avionics, it's just the job of validating requirements is just getting harder because there's less deterministic behaviors. And so we want to find a solution that allows us to verify the system requirements and validate that software designs can meet their real-time performance goals. So how do we solve this problem? Of course, we want to center it around AADL, just like many of you have mentioned today. We want to use a model-based systems engineering technology. And so part of that solution, you would use a system defined in AADL. And in the AADL model, you will have input data from the avionics system. Now you could also use possibly live data from a hardware in the loop scenario. And what would you like to get out of the solution? You would like to get your model behavior parameters, things like data flow rate averages and variances. And then also you want to get data analysis results to show how well your critical tests were executed and how many deadlines you met and how many were not met. So our goal is to model the inputs, outputs, and the interdependent processing of a given system, especially to model the negative effects that contribute to the non-determinism of multi-core systems, such as the ones you see up here: buffer overflows, bus transmission delays, contention over memory, such as cache misses, thread preemption, and processors that are busy. Another goal is to provide data analysis of these negative effects to help validate the performance requirements and designs. So our solution, Drew mentioned, is called Assist. So what is our solution? Assist allows us to better analyze real-time performance requirements using simulations of representative use cases defined in the AADL language. What is our approach? We use a discrete event simulation engine that can model avionics systems of systems specified in the AADL language, which can use data sources that are either internal to the model or we can also use external or hardware in the loop data sources as stimuli for the simulated processing. And Assist can simulate at any time resolution down to the picosecond level. Assist can be used to iteratively refine a system so that you can get closer to meeting your requirements. In the future, we hope to automate this refinement sorry. The assist output then becomes the revised system model as a result of the refinement and the data analysis reports that show that there is a match between your specification requirements and the expected performance, or that there's a mismatch and the component specification violations are identified. All right, this is a diagram of our product line. We're currently completing our baseline simulator on the left. That's our core simulation engine. We're simulating AADL components, subcomponents, and various attributes of the AADL language. In the middle, you see our unified error and behavior analysis capabilities. We demonstrated a proof of concept for the unified error and behavior analysis, and we intend to move forward with that with phase 2 effort. And on the right is the change impact analysis. This is where if we want to analyze if you change part of a system, how does that ripple through your system, or what effects are caused by what effects in your system are caused by one change. And then we also have a what-if analysis feature, which allows us to optimize over several parameters. And these efforts on the right, these were just starting to work on. So these are the sys components these are the AADL components that we can process in Assist. We can process software components, hardware components, and properties of these components. Mostly we deal with timing concerns, such as compute execution times and deadlines. And we also analyze the component connections, such as data flows and connections through ports. And so this is just a list of the AADL components and properties that we support. I won't go through all of them. We are missing things like just a few things, virtual processors and modes, but we intend to finish those features by the end of this phase. This is our high-level architecture. You can see on the left we have our AADL system configuration that defines your system and the interrelationships between your components. And you also have optional live sensor data or hardware-in-the-loop data feeds. In the component management area, that's where we parse the AADL file and we instantiate instances of the system components that you've specified. And over here in the simulation models, this is essentially our simulation engine, and this is a sampling of, one use case where we're instantiating a multi-core system. And then on the right, you can see we collect statistics of our simulation, and we store it in a time series-based database that can be viewed on your web application, either in a live scenario, or you can review the data later. So this speaks to the motivation for developing Assist. There's a FAA study that focused a lot on interference, how interference channels in multi-core systems lead to non-determinism, and that makes it difficult to validate system requirements and design performance expectations. And in the next bullet, you can see these are the statistics recommended by the FAA to be collected, and they are collected by Assist. We have our core processor utilization, processing time, cache misses and hits, thread executions, and deadline violations and flow rates. Okay. This is the demonstration scenario we've set up at the table in the exhibition space. We have a simulated sensor feed that's feeding into a modeled flight recorder. And we have two scenarios. We have a dual core system, and then in that system also we've added a video processing functionality to that scenario, and we've done the same thing to a quad core system, and we can demonstrate the differences or the data analysis results between the two systems. So here it is graphically. As I said, there's sensor data feeding into our simulator. There's also a video camera feed feeding in a live video feed, and then all the results go through a database, and then you'll see the results on the web display. Okay, accelerate. So this is the dual core graphs, similar graphs for a quad core. And this is the analysis of the graphs. Basically, you can see the quad core has more headroom. And then in the thread preemption latency, there's it's kind of a little deceiving, but you can see the axis on the right side is very small numbers. So essentially, there's much less latency instances caused by thread preemption in the quad core system. And then we have process deadline violations. There's much less violations on the quad core, where on the critical tasks are more like the purple colors on the left, and you can see there are no violations on the right. These are some of the challenges in the development of our system. The top bullets, those are the challenges we've overcome, and then the bottom three bullets are challenges we still have to meet, but we're pretty confident on overcoming these challenges. What are our next steps? We hope to implement virtual processor partitioning, generate additional summary statistics, and we'd also like to implement the analysis of more AADL parameters or properties, and then also implement the simulation of different types of peripherals and simulation of different languages. And we hope to improve our GUI, and we also have a cloud infrastructure that we're working on. Currently, we've simulated those two use cases in the cloud, but we also would like to explore a cluster solution, and we're currently working on deploying on Kubernetes.